Hi everyone, welcome to my YouTube channel, and in this video we will talk about the third iteration of our series in our unique path. So this problem is 980 from the Leetcode, and let's look at the problem. Here is the problem, and I want you guys to pause this video to come up with your own solution before we look at my solution together. The first approach, like interval setting, is you can come up with backtracking. I think this is the first approach that I will try when I'm in an interval setting. Here in this problem, we have to think. So we have to find the total number of unique paths starting from our initial position, like where this robot is. So starting from where this robot is and all the way to this where flag is, right? In our grid, it is represented by 1 and 2 respectively. So let's look at the robot's location. That would be this guy. And then you want to count how many unique paths there is to get to this guy. And then we have to visit all this empty block, like square, exactly once. Not only do we have to visit all empty square, we have to visit them exactly once. So that's the only difference that makes this problem a little bit more difficult than the previous two problems. But I think this is not too difficult, and let's look at the solution. So we will be running function recursively. We will have some recursion going on, so we have to track how many empty square we have visited so far and how many of them are unique, right? Say when we are in the in this boundary, and then we notice that our two neighbors are invalid, so that means we have to look at these two guys, and then this one is already visited, so we cannot go back to this guy, and then we can only visit this guy if it is not visited. So how do we make sure that we are only visiting the empty square that we haven't visited beforehand? You can create, I would say the easiest way is to make an in-place modification to our input. In this case, that would be grid, this guy. So if you look at this one, the check mark means that we already have visited, and this green robot means that we are at here. This is our starting point. That means we have already visited like these points, and then we change that value to -2. As long as it is not 0, 1, 2 or -1, it is fine. This means that our robot is here and we have visited all these points, and then we look at its neighbor, and this is our exactly what we wanted, destination. And then we have to keep counting how many empty square we have visited. So that's something that we also have to keep in mind. And so that's our number _0 whenever we run our function recursively, and when we also have to do the backtrack. Like in this case, when we see that this is our destination, that means we have to backtrack, right? When we do the backtrack, we have to make the we have to undo the change, because when we are visiting when we are visiting say empty square, we are changing the value of its grid to -2. But then when we are backtracking from that position from here to here, then we undo the change and we set this equal to 0. So that's something that you have to keep in mind. And we also have to increment and decrement our this count variable number _0. So when we backtrack, we have to decrement this by 1. When we encounter this, when we run our backtrack function and that we haven't visited before, we have to increment that count this number _0. So let's look at the code. And this is the code. The first thing we do is we have to find how many empty square we have in our grid, and then when we run this for loop twice, we also find where is our starting position. So that's what's going on here. So this is like O of n square. N is the size of this matrix, and then we have this helper function, and this is the one where we will be doing the backtrack, etc. So initially we set answer equal to 0, and this is the answer that we will return here. And then we increment this our current _0. That's how many empty square we have encountered so far, and then we increment this by 1, and notice that this one, even though it is like 1, we can consider that initial position is also empty square. So once you do that, we have to so this is something that a little bit tricky, but when we run this function, our current, like if you look at here, our parameters are start underscore x, start underscore y, and then we have -1. If you put 0, this will not give you the right answer, because we have to put -1 because we consider this one as empty square, even though it is technically not. And once we make the change, we first store our initial value in this case. So there will be, let's say if you are here, then our temp variable will be 0. So temp will be 0, and then when we backtrack, we undo the change, and that's given by this line of code. And then we also have to decrement our current underscore 0 by 1. Now we look at the neighbors, like, so we'll be looking at its 4 neighbors. We have new underscore x and new underscore y is like these 4 choices, and then we'll be trying each choice and see if we can go to the next one. So we want to check that new underscore x and new underscore y are within this grid that's given by 0 less than or equal to, and then less than, so blah blah blah. And then we also have to do like another check. If the grid value at new underscore x comma new underscore y is equal to 0, then what do? We run our function again, and then we increment our answer variable by this much, whatever return value we get. Otherwise, if the next neighbor is our final destination, and we also have to check that current underscore 0 is equal to numbers underscore 0, right? This is the total number of like empty squares we have seen so far, and then numbers underscore 0 is the total number of empty square we have in our grid. And if this is if they are equal to each other, then okay, then we have so far found one unique path, and we increment our answer variable by 1. And then when you exit this for loop, that's when we are backtracking. When you do backtrack, we have to undo the change here, and then we also have to decrement our current underscore 0 by 1, and then we return our answer. So that's the first approach. I hope this makes sense, and let's look at the second approach. So this is bit masking, like using dynamic programming. And I know bit masking, like bit sounds a little bit like difficult, but it's just like bit masking, like it is just like, say we are using like binary number to count, like to determine whether we have visited like this coordinate or not. Why do we use bit mask and dynamic programming? Well, it has better time complexity. That's something that I will get to this point later. So that's the key part. And as in all the dynamic programming problems we have seen so far, we have to define what is our DP exactly and how many states are involved. We have 2 states, right? In this case, how many states we have visited. In this case, state means like this guy, coordinates, like empty square. So how many empty square we have visited, and the position like I comma j that we can get to. So our DP has 2 states, and this is like this, DP of how many states we have visited and I comma j, and that is equal to a total number of valid paths to reach I comma j from starting position, like starting where like this pink robot is. And then bit mask is used in how many states we have visited part. So let's look at this guy, this example. Like this one is like this is just some label like 0 1 2 3 4 5 6 7 8 9 10 11. This is our grid indicating which one is empty squares or not. This is just some label, like the label of these squares. So we'll be going this way, and let's say we have visited like this, like 3 green squares. You can use bin operation to do this. So this is how we do this. Initially we set this bit equal to 0, and then we to carry out this operation. And when you, like say in Python, when you type this, we get something like this, like 0b101000 and then 10. And you may be thinking, what does that really mean? How does that really help us? Well, see where ones are located, right? So this is the first position and this is the second position, right? Here is our second position, and that's where we have just visited. Third, fourth, fifth, sixth, seventh, and eighth. This is eighth. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then 9 and 10th. So this guy. So we notice that this, where ones are located, it tells us where we have visited so far. And that's a very key point. So this is what I mean by this. And that we can use a binary number to mark the first bit equal to 0. Actually, yeah. So first bit in this case, because we are, so in this case, suppose we visit 0, 0, so we mark the first bit equal to 1. So in that case, this one will be 1. And then we only care about the letters, like the string that comes after 0 and b. So all this like 1, 0, 1, 0, this part, we don't care about these two guys. So that's how we mark the position that we have just visited, or we have visited before. We have to check, how do we check whether we have visited these squares when we run our functions? So how do we check we have visited, like like say these squares beforehand? So we can also use this binary number to see if we have already visited its neighbors before. And let's say, for example, our robot is like this guy, and then we have visited these green squares, and we want to know if we have visited like 1 or 4 before. So how do we do this? Well, we use this function. We have, and then we use like bit, like this one, and then we have 1, and then we have this end, and we have 1 here. When you do this, now it checks whether, so you will get either 0 or 1. This like the output of this guy will be either 0 or 1. We check if these are 0 or 1, and if it is equal to 1, what does that mean? That means we have already visited, so we don't go to that direction. If it is equal to 0, then it is safe to visit that position. So that's the key point behind this. And if you look at my code here, so one is the backtracking approach, another is bitmasking DP approach. They are very similar, but here you have this part going on where we have this I times column plus j. That's how we like mark the this bit equal to 1. So we set that equal to 1, and then we count how many like the string ones we have seen so far. This is another way of saying, like, so this part will be equal to this part. And code is pretty identical, except that we are here using, of course, memoization. And then our states, here we have binary of bit, and then we have I comma j. And yeah, so the only difference here is that the time complexity for backtracking approach is 3 to the power of k. K is the size of the grid, and in this case it will be row times column. And why is it 3? Well, you can visit 4, but at most we will be visiting 3, right? We have 4 neighbors, but other than the first guy, right, other than this guy, we will be only visiting 3 of its neighbors at most. And actually in practice, like in this problem, you'll be way less than 3, because some of them will be we have already visited, and some of them is like, say, like we have a block, so we cannot go through. But anyway, the worst case scenario, we have a 3 to the power of k. But for bit masking DP approach, we have time complexity of k times 2 to the power of k. When k is large, this one is faster than this. But for this problem, I think since the size, the input is what? We have a very small input size, so the time complexity shouldn't be that much like different from each other, but I just want to point this out that the time complexity of bit masking DP approach is way faster than the backtracking approach if the input size is quite big. So anyway, that's for this, and let's look at the code. And yeah, let's look at the code. Okay, so we have two codes here, so let's run the bit masking DP first. So that's this part, and let's run this. All right, so that's for the bit masking DP approach, and let's run the backtracking approach. So yeah, so those are these, like we have, so that's for these two approaches for solving this problem. And as you can see, the size of this, the grid is not big enough, so I don't think these two approaches are that different. But if the input size is very big, the difference in time complexity is quite huge. So that's for this video, and I hope my video helps you guys understanding this problem. Don't get scared about I just hope that you guys don't get scared about using bit masking to solve some problems, because bit masking really helps a lot. It really helps. And yeah, so that's for this video, and I hope you guys have a great weekend, and I will see you next time. All right, bye bye.